Welcome back. Today I'd like to talk to you a little bit about planes and surfaces. So I want to start with just kind of the most simple surface that you could possibly have, and that is a plane. So let's start out by drawing a plane. Okay. So obviously the plane doesn't end at these boundaries. The plane keeps going in all directions infinitely. So this plane keeps going in all directions, and so here's our plane, and our question is here, what is the equation of that plane? So there's a couple pieces of information that it would be nice to know about this plane that's going to help us as we kind of look at it. The first one is we can talk about a vector that is perpendicular to the plane. So if I have this plane, I could, let's say here we have a point on that plane, and we have a vector pointing up from that plane at an exact right angle, okay? And let's call that vector in for the normal vector to that plane. So you could set that normal vector anywhere on that plane, and it would still be normal to that plane. Okay. Second thing I'm going to write is, let's say that we also know a vector that's on the plane. Okay, and the way that I'm going to set this up is over here. Let's call this point P sub 0, which is x0, y0, z0. And let's say that that point, we have a vector that points to another point on the plane. It doesn't really matter where. So we have a vector that points to another point on the plane. And let's call this second point P, which is x, y, and z. Okay, so the first thing that I'd like you to notice is that the vector that's sitting inside the plane, that one would be called P0, P. That's the vector that's sitting on top of the plane. We could dot that with the vector in, right? And what should we get out? Well, we should get out 0. Why do we get out 0? Because we can see that if we moved this vector right here over, this is exactly perpendicular to the vector in. And if I dot together two vectors that are perpendicular, I should get out 0. So we see that any vector in the plane dotted with a normal vector to the plane is going to give me 0. Okay, that should be helpful. Second thing is I could write this vector in. I'm not sure what the vector in looks like at this point, but I could write it for sure this way. It's A in the I direction plus some constant B in the J direction plus some constant C in the K direction. Now let's write the other vector, which is P0, P, which is going to be equal to, well, it is x minus x0 in the I direction plus y minus y0 in the j direction plus z minus z sub 0 in the k direction. Now, I set up here that if I dotted those two vectors together, then I should end up with 0. So let's dot those two vectors and see what we get. Okay, so to dot those two vectors together, then I want to take the I component of each and multiply them together. So I get x minus x0 times A plus, now multiply the j components together, which is y minus y0 B, and then we'll multiply together the z components, which or the k components, z minus z0 times c, and we say if I dot those two together, then I should get 0. Okay, so what I end up with is there are really two ways that I could write this. Typically, we pull these constants out in front and we write a x minus x0 plus b times y minus y0 plus c z minus z0 is equal to 0. That's one way to write it. But I could also multiply through by a and b and c and distribute those, and I'd get something like this. ax plus by plus cz, but then all of these others, a times negative x0, I could move to the other side, and I get a x sub 0, and I get plus b y sub 0, and I get plus c z sub 0. Also, what a lot of people will write is something like this. ax plus by plus cz is equal to d, where d is just a constant, because remember x0, y0, and z0, they are just constants as well. So this would be the general form of a plane, as would this. Both of these are considered general forms of a plane, where I know 2 points in the plane. Actually, I really only need to know one. I need to know x0, y0, and z0. And x, y, z is just a random other point in the plane. Now, notice, though, that if I kind of want to get a general form, a big piece of that general form is a normal vector to the plane. So a, b, c, that was my original normal vector in component form. So that is helpful to us. Let's do an example and kind of see how this works. So, quick example. Find an equation for the plane through point A, which is 0, 0, 1, B, which is 2, 0, 0, and C, which is 0, 3, 0. Okay, so if you have three unique non-collinear points, there's exactly one plane that goes through them, and so we'd like to determine what that plane is. So to do that, what would be really great is to know a normal vector to that plane. But think about it this way. If we have these 3 points, A, B, and C, and they are all in the plane, then if I could find a normal vector to the 2 vectors AB and to the vector AC, if I could find a vector that's normal to both of those, then it would have to be normal to the plane as well, because both of those vectors sit inside the plane. So the only vector that would be normal to 2 vectors that sit in the plane would be the normal vector. Okay, so let's do this. So AB is equal to, well, what is it? It is 2 minus 0, which is 2, 0 minus 0, which is 0, 0 minus 1, which is minus 1. And now let's look at AC. I got 0 minus 0 is 0, 3 minus 0 is 3, and 0 minus 1 is minus 1. So here are 2 vectors. Both of these vectors, AB and AC, live in the plane that I'm looking for. So what I want to do is find a normal vector to both of those vectors. Well, the way that I find a vector that's perpendicular to two other vectors is I cross those two vectors together. So let's find the cross product of AB cross AC. The way that I find a cross product is I take the determinant of the matrix IJK 2, 0, minus 1, 0, 3, minus 1. And now I can use the horseshoe method to figure this out. I get I times 0 times minus 1 is 0. Then I get j times minus 1 times 0 is 0. And then I get 2 times 3 times k, which is 6k. All right. Then I go the other direction. K times 0 is 0. 1, negative 1 times negative 3 times I, and then I need to multiply it by an additional negative 1 because I'm subtracting here. So this is minus 3i. And then I get j times 2 times negative 1, which is negative 2j. So this normal vector, let's call it in now, that's normal to my plane, is how many i's? I suppose this is 3i plus 2j plus 6k. And now we have a normal vector. So we're very, very close. So I can use really any point. See, what I need to find the equation of a plane is I need a normal vector. Well, that's good because I have a normal vector. And I need a point that's in the plane. Oh, I have 3 of those, A, B, and C. Which one should I use? How about B? Because it's simple, 2, 0, 0. So we'll use this normal vector in, and we'll use this point that lives in the plane B to find the equation of the plane. So what I've got is that I get A, which is the first component of my normal vector. So it's 3. And maybe I should just write real quick before I get to writing this. What is my standard equation again? It's A, x minus x0, plus B, y minus y0, plus C, z minus z0 is equal to 0. And I can use this to find the equation of my plane. So A in this case is the first component of the normal vector, which we know now is 3. So this is 3 times x minus x0, and that point I chose to use was 2, 0, 0, so this is 2, plus b, which was 2, times y minus y0, which was 0, plus c, which was 6, z minus z sub 0, which was 0, is equal to 0. And now we can simplify. We get 3x minus 6 plus 2y plus 6z equals 0. And if you like, you could move that negative 6 to the other side and get that 3x plus 2y plus 6z equals 6. And this would be the equation of the plane that passes through those 3 points. If in doubt, test the 3 points, right? Plug in the 3 points for x, y, and z here and see what you get. One of the points, right, that we wanted this thing to go through was the point 0, 3, 0. So if I plugged in 0, 3, and 0, what would I get? I would indeed get 6. So it works. And it works for all 3, and so I'm confident in my answer. Okay, let's do another example. Second example. Let's find a vector that's parallel to the line of intersection of the planes (3x minus 6y minus 2z is equal to 15, and 2x plus y minus 2z equals 5. Okay. So the first thing that you should notice is what happens when I intersect two planes that are not the same plane. So let me draw two planes here. Here's a plane. And then let's draw another plane that is crossing through this plane. And it has some line of intersection in between those two. What I would like to do is I would like to find a vector that is parallel to this line of intersection right here. Okay. Now, first of all, I guess I should say, well, what do I know about these planes? Not a lot. I know their equations, but I also, because of their equations, I know normal vectors to each of those planes. So the first plane has a normal vector coming out of it, right? A normal vector coming straight out of it that is perpendicular to the first plane. And then the second plane has a normal vector coming out of it that's perpendicular to the second plane. Well, what if I was able to find a vector that was perpendicular to both of the normal vectors? Well, if it's perpendicular to the first normal vector and the second normal vector, then it must either point this direction or this direction. Either way, it is parallel to that line. Okay, so in other words, if I could find a vector that's perpendicular to the first normal vector and the second normal vector, then I've got what I want. So really, I just need to cross the two normal vectors, and then that will give me my answer. What are the two normal vectors? Well, the first normal vector is just the vector 3 minus 6 minus 2. And the second normal vector is 2, 1, minus 2. If I cross those two vectors together, I'm going to get an answer to this problem. Okay. So let's cross those two vectors together. So I want to take the determinant of ijk, 3 minus 6 minus 2, and 2, 1 minus 2. And what do I get? I get, first we multiply this way, and I get 12i. Then we go here, and I get minus 4j. Then I go here, and I get plus 3k, minus, now we subtract, and I multiply here, which gives me minus 12k. Then I go here, and I get minus 6j. And then we add negative 2i. And now we can simplify. So we get 12 i's plus 2 i's is 10i. Then we get minus 4j plus 6j is plus 2j's. Then we get 3k's minus 12k's is plus 15k's. Okay? And this is going to give us a vector that is parallel to the line of intersection between those two planes. So that's kind of cool. Okay. let's try one more example. So where does the line x equals 8/3 plus 2t, y equals negative 2t, z equals 1 plus t, intersect the plane 3x plus 2y plus 6z is equal to 6. Okay, so what we need to do is we see this is an x, a y, and a z, and I know what x, y, and z are. So let's go ahead and replace x down here with x up here. So we get 3 times x, but x in this case is 8/3 plus 2t. So I'm just going to replace it with 8/3 plus 2t plus 2 times y, but y now is negative 2t, and then plus 6 times z, but z now is 1 plus t, and I know that that's supposed to equal 6. So now let's simplify this a little bit. I multiply 3 times 8/3 and I get 8 plus 6t minus 4t plus 6 plus 6t equals 6. Combine the 6's, I get 6 minus 4 is 2 plus 6 is 8t, and then I get 8 plus 6 is 14 equals 6. So 8t is equal to negative 8, and t is equal to negative 1. So now all that's left for me is to plug in t equals minus 1 to this original line and see where I'm at on the original line. So if I plug in t equals 1, what do I get? I get that x is equal to 8/3 minus 2. Well, what's 8/3 minus 2? This is 8/3 minus 2, which is 8/3 minus 6/3 is 2/3. Y, I plug in minus 1 and I get minus 2 times minus 1, which is just 2. And then z is going to be 1 plus minus 1, which is 0. So the point that I'm looking for here is 2/3, 2, 0. And this is my answer. 2/3, 2, 0 is the point where that line and that plane intersect. Pretty cool. Okay, the last thing that I kind of want to talk a little bit to you about, and I'm not going to go into great depth on this, is just the idea of a cylinder in space. And then the second thing is that there are all sorts of interesting shapes in space. Okay, so let's start out with the definition of a cylinder. A cylinder is a surface that is generated by moving a straight line along a given planar curve while holding the line parallel to a given fixed line. Now, when most of us think of a cylinder, we think of the following. We think of something that looks something like this. That's a cylinder, right? Well, sort of. A cylinder is this, but I would say not quite. A cylinder in 3 dimensions actually should keep extending up and down infinitely in 3 directions. So really what we're doing is we're taking a straight line. Let's say it goes through these points. Straight line. And then we're letting it turn around this circle. Take a straight line and let it spin around in a circle, and you get a cylinder. So really what it is it's a straight line that's being moved along a curve. Now, this is every bit as much of a cylinder. Let's take a straight line. Here's my straight line. And I want to move it along a parabola. Okay, if you move a straight line along a parabola, then it's going to give you something that looks sort of like all of these. So it's curved, this curved space, it keeps going along this parabola. So it's a bended sheet is the way that it would look. But you just take that straight line right here and you move it along the parabola and you get this kind of bended sheet. Okay? That also would be considered a cylinder. It's not this nice circular cylinder that we're used to. This is what we would call a circular cylinder. But it's still a cylinder. We're not going to use this a ton in this class, but it's good to know that when somebody speaks of a cylinder, you might have to ask them the question, is it like a right circular cylinder, which is what we would be talking about over here, because this is also at a right angle to the circle. It could be, it could not be. Okay. So we could come up with all different shapes of cylinders. This one just happens to be circular. All right. Also, I want to mention that there are tons of different types of curves in space. Okay, and I'm not going to cover them all right now, but as we move through the course, you may want to become familiar with them. Also, on page 869 of the book, so page 869, I would look at this and see some of these different shapes. Some of the ones that you should be familiar with is like, what if you take a parabola? Okay, let me draw my three-dimensional coordinate system here. So here's 3 dimensions, and let's say I have a parabola in, this is my x, this is my y, this is my z. Let's say that I have a parabola in the YZ plane, and then I let that parabola spin around the z-axis. Okay, if I let it spin, then it's going to fill in all of this. And back here, I can fill in dotted lines. And you get this shape that kind of looks like a hill turned upside down, but it goes up forever. We call that shape a paraboloid. Okay, so that is what we call a paraboloid. And I'm not going to go through every single one of these shapes. We could talk about a hyperboloid, which is really just a hyperbola that is spun. If you spin the hyperbola, then you're going to get this shape that kind of looks like a vortex, and this is what we call a hyperboloid. One that's quite interesting is that we could get what we call a saddle point. Okay, a saddle shape happens when you get kind of a parabola going in one direction, in one axis direction, and then you get a parabola going in the other direction here. So in this way, we're getting parabolas curving up, and in the other direction, we're getting parabolas that curve down. And so on the other side, we might have. So we kind of get these things curving down in this direction, but things are curving up in this direction, which creates at this point right here what we call a saddle point. Because you can kind of, when you start visualizing this shape, you can see it's kind of like if you were to sit right there, it'd be like sitting on top of a saddle. So we call this point right here a saddle point, and that's something that we'll use in the future as well. Okay, so look through all of those shapes and just get familiar with the equations of those different shapes. I may bring some of those shapes up in the future, and it would be nice if you were at least familiar with what I'm talking about. So we should know what an ellipsoid is, an elliptic paraboloid, a hyperboloid, an elliptic cone, a hyperbolic paraboloid, all of that. You should kind of know what I'm talking about. So look at the pictures. This isn't anything super complicated, but just get a feel for those. Okay? And I think that that's all we need to do for today.